Lesson 1, the turbine engine. The sound of the turbine engine indicates that it is rotating at a very high speed. To operate at a very high speed, the engine must be built to critical tolerances and employ several methods to keep the rotating parts together. In this lesson, we will be observing the building of an engine to give you a better understanding of the rotating components. When you have finished this lesson, demonstrate your understanding of the material by taking the progress check on the following performance objectives. First, describe the assemblies used to hold the rotating engine parts together. Second, identify the two sections of the rotating shaft. Here is your instructor.
We are in the engine build area where we will be observing the assembly of several Centaur engines. All of the parts for these engines are shipped to this area inside these transport cases. The parts are made from high-temperature alloys and have been fabricated or machined to tolerances which permit extremely high speed and temperature operation. Each part and assembly has been balanced for vibration-free operation. As the engine is built, the balance and tolerances of the parts is checked repeatedly and recorded for future reference. The engine assembly begins with the air inlet housing. The engine is built in a vertical position on an elevator beginning with the air inlet housing. Each successive piece is lowered in place until the engine is completed. The next step is the addition of the variable guide vanes. The inlet guide vanes are lowered onto the air inlet housing and positioned into place by the long rods. A magnetic pickup is located on the top side of the inlet guide vane where the wires are hanging. As you may recall, this is the backup overspeed pickup, G353. This pickup senses the rotating speed of the first stage disc assembly and will cause the engine to shut down if it senses 110% engine speed. Finally, the inlet guide vanes are seated and secured. Next, the compressor cone and first stage disc are installed as one unit. The compressor rotor forward seal is on the front end of the nose cone and keeps oil from flowing into the compressor. The compressor rotor tie bolt and center stud will run through the center of this assembly and connect the reduction drive gearbox. After the assembly is seated, a measurement is taken. The mechanic will take several measurements to check clearances and fit while building this engine. Each measurement is then recorded in a special book for future reference. The inlet guide vanes are completed when the third stage variable vanes are secured in place. You may recall that the variable guide vanes are used during acceleration to prevent engine surge. The next component to be added to the engine is the fourth stage disc assembly. It is carefully seated on top of the third stage disc by matching marks on each piece to assure the balance of the completed rotor. These teeth are part of a curvic coupling that is between each disc. Two discs will mesh together and are prevented from slipping by the teeth of the curvic coupling. The mechanic is now ready to install the compressor case onto the engine. The successive compressor disc and stator assemblies will be built up inside the compressor case. The clearances between the rotor components and the case are continually checked to make sure the fit is within the tolerances permitted by the design specifications. Let's take a closer look at the compressor rotor components. The disc assembly is the rotating wheel with blades. A spacer fits between each disc to provide a smooth path for the air to flow over the curvic coupling, which is located in the center of the assembly. The mechanic builds the compressor up by adding a disc followed by a stator and a spacer. After each disc is seated in place, the fit is checked by the mechanic. Each disc assembly has match marks indicating how the assembly must be fit together to maintain the balance of the complete compressor rotor. These marks are being checked now. If they do not match, he will rotate the disc to obtain the match. After the 11 discs have been installed, the 11th-stage stator and exit guide vanes are seated into place. The exit guide vanes will condition the air for the combustor. Next, the diffuser is mounted onto the compressor case. It's secured in place with special bolts to prevent it from coming loose during operation. After the diffuser, the compressor bearing support housing is seated with the radial bearing. The engine is now ready for the compressor rotor tie bolt. The engine is placed in a horizontal position and the tie bolt is inserted through the air inlet housing. Next, the tie bolt is physically stretched with a hydraulic jack. When the bolt is stretched to the necessary distance as indicated by the wire feeler gauge, the securing nut is tightened. When the pressure is released, the clamp of the bolt will hold the compressor rotor section together. The next step in the building process is to measure the in-play of the shaft. A dial indicator is used to measure the play in the shaft. If the measured play is greater than the tolerances, corrective measures will be taken. The measurement is recorded in the engine build logbook for future reference. This logbook can be consulted if a problem should arise with the engine during its initial testing. The next step is to build the combustor section before it is installed on the engine. The combustor liner is lowered into the turbine bearing support housing where it will rest until the fuel injectors are installed. Next, an RTV sealant is applied to the mating surface of the bearing housing to form a tight seal between the housing and the combustor case. The combustor is now ready to be secured in place. 10 fuel injectors are used to hold the combustor liner in place. The mechanic lifts the liner up and inserts a fuel injector into the port on the combustor liner. You should never remove all the fuel injectors at once, as they are the only items holding the combustor in place. A keeper is inserted into the turbine bearing support housing, and then the support housing and combustor section are installed on the engine. The combustor assembly includes 3 of the fuel injectors and the fuel manifold. The engine now includes the air inlet housing, compressor section, diffuser, compressor bearing support housing, turbine bearing support housing, and the combustor section. The turbine rotor shaft is inserted next. It is lowered through the center of the combustor and onto the end of the compressor rotor shaft. Support for the shaft is provided by the turbine rotor bearing, which was inserted with the turbine bearing support housing earlier. Note the curvic coupling for the turbine wheel on the end of the shaft. The next step is to secure the compressor rotor shaft to the turbine rotor shaft. The engine is again placed in the horizontal position. The center stud is inserted through the center of the air inlet housing and through the hollow center of the compressor rotor tie bolt. The center stud is then secured into the turbine rotor shaft. A hydraulic pump is used to stretch the center stud to increase its clamp. The next stage of the engine assembly is the turbine section. The turbine wheels have already been assembled with the blades fit into slots around the wheel. A notch in the shape of a fir tree is made at each blade location around the turbine wheel. On the root of each blade, that shape is duplicated and fit into the slot on the wheel. The slot on the wheel is slightly larger than the root of the blade, which allows the blade to expand during engine operation without cracking the wheel. The blade is actually held in place during rotation by centrifugal force of the rotating wheel. After the turbine nozzle support case and the first stage turbine nozzles have been installed, the first stage turbine wheel is ready to be seated on the turbine rotor shaft. The curvic coupling of the shaft and the turbine wheel mate to form a non-slipping connection. Assembly of the second and third stage nozzles is completed in the engine build area by the mechanics. Each of the nozzles is individually fitted to the stationary disc. The entire assembly is placed into the turbine nozzle support case. The next component after the third stage turbine wheel and the third stage turbine nozzles is the wheel shoe. The shoe forms a seal around the outside of the turbine wheel, keeping the air from escaping around the edges of the blades. The last component to be added to the engine is the turbine tie bolt. The bolt is inserted through the center of the turbine wheels and secured into the end of the turbine rotor shaft. A heater is then inserted into the hollow center of the bolt, and the tie bolt is heated until it expands to a specified length. Then it is torqued down again to increase its clamping force. The assembled engine is now ready for mounting on the skid. The cold end of the shaft will be connected to the reduction drive assembly, where the rotational power will be reduced for the generator and the accessories.
You have just viewed the lesson on the turbine engine. Let's review the important points. The turbine engine consists of two major rotating sections. The first section of the engine to be completed is the compressor section. The rotating parts of the compressor include the disc assemblies, spacers, and the compressor rotor shaft. The second major rotating section is the turbine rotor, which includes the turbine rotor shaft and the turbine wheels. The center stud runs the length of the engine and holds the rotating parts together. The rotating parts are kept from slipping by the use of a curvic coupling between rotating parts. You have just completed this lesson. Now turn to your learning guide for review. If you wish to test your understanding, stop the tape and take the progress check. Lesson 2, Reduction Drive Assembly. When this engine reaches 100% speed, it will be rotating at approximately 15,000 RPM. The engine must rotate at a high speed to cool the hot section, to keep air flowing through the compressor, and to run efficiently. Engine speed is reduced in the reduction drive assembly for use by the generator and accessories. When you have finished this lesson, demonstrate your understanding of the material by taking the progress check on the following performance objectives. First, describe how the engine's high speed is reduced for use by the generator and the accessory units. Second, describe the function and location of the two magnetic pickups. Here is your instructor.
This turbine engine is used to drive the generator located on the forward end of the skid, and to drive the various accessories associated with the package. The engine's rotational speed of 14,951 RPM must be reduced to 1,800 RPM for the generator and even further for some of the accessories. Speed reduction is accomplished here in the reduction drive gearbox. This reduction drive assembly uses a gear arrangement referred to as a compound epicyclic star. The name comes from the gear's resemblance to a solar system. The central gear, or sun gear, rotates the three star gears that are placed around the sun gear. Let's move out into the shop and take a closer look at the reduction drive assembly. These are the two major components of the reduction drive assembly: the ring gear and the planet carrier with the sun and star gears. The input shaft located here is connected to the engine and the sun gear. As the input shaft rotates with the engine, it turns the sun gear. Its teeth mesh with those of the three star gears located here, here, and here, causing them to rotate. Notice how the star gears have a large and small diameter gear. This large diameter gear meshes with the smaller sun gear, and the smaller side of the star gear meshes with the ring gear. The ring gear fits over the 3 smaller star gears powered by the 3 star gears. The ring gear turns the output shaft, which is connected to the generator. There is also a driver gear connected to the output shaft, which operates the accessory equipment, such as the lube oil pump and the servo oil pump. During the start sequence, the intermediate gear is rotated by the starter. The rotational motion is then transferred through the reduction drive assembly, the driver gear, ring gear, star gears, and sun gear to the input shaft, which rotates the engine. I mentioned earlier that the engine speed must be reduced for use by the generator and the accessory equipment. Speed reduction occurs at 2 places. First, speed is reduced between the sun gear and the large diameter of the star gear. The smaller sun gear must rotate approximately 2 1/2 times to rotate the star gear 1 time. A second speed reduction occurs between the small diameter of the star gears and the ring gear. The smaller star gear must rotate approximately 3 1/4 times to rotate the ring gear once. An engine speed of 14,951 is effectively reduced in 2 steps to 1800 RPM on the 60 Hz application generators. Another important component in the reduction drive assembly is the magnetic pickup. You may recall that magnetic pickups monitor engine speed and produce an AC signal which is proportional in frequency to the speed of the engine. There are 2 magnetic pickups on the reduction drive assembly. Magnetic pickup G383 is located on the right side of the assembly here. It measures engine speed and sends a signal to the engine speed control Z183. Magnetic pickup G351 is located on the left side of the assembly and sends a signal to the electronic load speed sensing control unit Z251. A third magnetic pickup, G353, is mounted on the variable guide vane support ring and sends a signal to the backup overspeed monitor Z253. Let's take a closer look at the operation of a magnetic pickup. The magnetic pickup is basically a magnet with a coil wrapped around the bottom third of the permanent magnet. The magnet forms a flux field extending from the end. Note that the magnetic flux field lines cut across the wires of the coil. The magnetic pickup is inserted through the gearbox and is positioned directly over a gear. As the gear moves, the gear teeth pass through the flux field and disturb the flux lines. The movement of the flux lines across the wire coil induces the flow of electricity to the control module. The frequency of the AC voltage produced by the magnetic pickup is directly proportional to the number of gear teeth passing through the flux field. Each time a tooth passes through the field, a complete cycle is produced. Therefore, if 101 gear teeth pass through the field, the frequency would be 101.
You have just viewed the program on the reduction drive assembly. Let's review the important points. The reduction drive assembly reduces engine speed for use by the generator and accessories. Speed reduction occurs at 2 points between the gears. First, speed is reduced between the small sun gear and the large diameter of the star gears. Second, speed is reduced again between the small diameter of the star gear and the ring gear. The magnetic pickups are used to measure engine speed and sense engine load. The magnetic pickup is a permanent magnet with a coil of wire wrapped around it. As a gear tooth passes through the field, an electrical current is produced which sends a signal to the control unit. You have just completed this lesson. Now turn to your learning guide for review. If you wish to test your understanding, stop the tape and take the progress check.